I'm going to introduce our next speaker, that is Matt Dawkins. Also, thank you, Matt, for being involved, because you are in New York, I think, and it's not a very good hour to to participate in this kind of forum, but I appreciate so much your involvement. Matt Dawkins is a senior R&D engineer at Kitware ENC in New York, as mentioned, for the US, and he's going to present the VIAME, an open source do-it-yourself AI platform and archive for environmental science. So thank you, Matt, and go ahead.
Yep, thank you. Hopefully you could hear me okay.
Yeah.
Perfect. I'll just share my slides here. Yeah, I have the opposite problem of Chris, so it's pretty early here, but it's not too bad. The sun's just coming up over the horizon.
Okay, perfect.
All right. So my name is Matt Dawkins, and I'm a software engineer at Kitware, a small software company headquartered out of upstate New York. And I'm going to start with a quick overview of VIAME, which is an open source toolkit that we've been developing alongside NOAA Fisheries, primarily in the US, but starting to branch out a little bit. Then follow up with some of the challenges we've faced. Some of these are solved, some not. Some of these are also shared by some of the earlier presentations. So first off, I guess, what is VIAME? Over time, it's evolved into a do-it-yourself AI toolkit that biologists can use to generate their own machine learning models with basically little or no programming experience, either in web or desktop interfaces. Additionally, recently, we've added an online repository for storing related imagery and annotations that some biologists have done on a few different problems with additional sort of limited support for training models. Most of its current use has been on the first three items on the list below, particularly object detection and tracking. But more recently, we've been expanding its capabilities into stereo measurement, image enhancement, registration, low shot learning, and some 3D scene generation. Lastly, it provides some tools for evaluating the performance of different algorithms, primarily detectors and trackers right now. But in both binary and source format, VIAME is released open source with permissive license. A portion of its algorithms are highly specialized to particular domains, such as some of the problems we see here with stereo problems, and not present in standard commercial offerings. But at the same time, some of its algorithms are very general purpose, so it can be used outside the domain for basically arbitrary image or video problems. For those not familiar with Kitware, we make open source software in a few domains. Some of our more well-known pieces of software is CMake, which is used as the build system and things like OpenCV, PyTorch under the hood, just for building on Mac, Windows, etc. We're primarily based in the US, but we also have an office in Lyon, France, a couple different offices in the US. I'm out of upstate New York, but also DC, Santa Fe, a few others. Kitware didn't fund VIAME, though, which was from a NOAA committee called AISI that was started basically in late 2015 with a representative from each fisheries science center in the US. The development picked up a bit more in 2016, 2017. VIAME wasn't the only product funded by ASI. Others include CoralNet, an open data store for coral annotations, and a couple more specialized applications. People have begun applying VIAME to a range of challenging problems, though. For example, here's some images from a few domains. We do a little bit with electronic monitoring, a bit more with underwater and aerial. So shifting gears a little bit. But then you also see some other applications like putting GoPros on penguin heads, so some surface-based applications. There's a range of data. A lot of the underwater ones necessitates running color correction because there might not be ambient lighting in those scenes. Aerial data might be from small drones, fixed-wing planes. Most of it's optical, but there's a little bit of infrared in there as well. So we've seen a couple different problems over the past few years that I'll highlight in the next few slides. Some of these have solutions, some don't. So I guess the first one is that we've just seen a very large, diverse range of users trying to use this software. Some are people with absolutely no programming experience, and then some are on the other end of the spectrum. They're highly technical. They want to modify their own things, interact with programming APIs. So to address this, we've created a couple different interfaces. The newest annotator we've been working with is called Dive, which can be run both on the web and the desktop. There's a instance of this hosted online at VIAME.kitware.com with some of the annotations that NOAA biologists have been generating. But one of its key capabilities is basically the ability to train models on multiple sequences at once, open them up in an annotator, supporting 3 types of annotation, so polygons, boxes, lines for stereo measurement. Secondly, in addition to that, there's more specialized interfaces like search for desktop search, multimodal annotation, and then lastly, programming APIs and project folders for training models outside of interfaces. So secondly, building off of that note, just the wide range of problems that biologists have brought into this and tried to solve with VIAME has necessitated creating multiple workflows for different type of paradigms. Sometimes people are fine spending several weeks sitting down and just doing annotations. Sometimes they're not. They just want to spend a couple of days. So trying to handle both of those cases has been important. Similarly, with the annotation front, sometimes people have time to do pixel level stuff, but sometimes they just want to do a first pass box level method. So trying to handle both of those. Another thing we've been trying to do is create larger ensemble data sets that we can use to basically bootstrap other people's annotations. So some groups have done a lot of annotation manually, others haven't, and they're just getting into it for the first time. One of our key aspects is trying to train generic models on just say fish that other people can apply to their data and try to clean up as opposed to doing it from scratch. In a traditional deep learning workflow, you annotate millions of annotations or hundreds of thousands, and then train your deep learning models. But our goal is to bootstrap that by introducing a model correction paradigm as opposed to just doing it all from scratch. Secondly, there's algorithm optimizations we try to do to handle this a little bit better so that people don't have to go in and tweak algorithms a bit more. So one is choosing when to automatically grid detectors over an image. On a lot of these aerial applications, the targets are really small. So you're going for things like endangered sea lions or seals and polar bears in the Arctic. So the pixel ratio of these targets are pretty small. So it tries to automatically grid up the image into individual tiles if needed. But then there's things like automatically handling learning rate adjustments and early stopping criteria, just so people who don't know much about deep learning don't have to go in and tune those things. Secondly, there's some automatic data fusion things. So basically taking a motion channel or depth channel, fusing that into your detectors for improved performance. Another problem I'm sure a lot of you are familiar with is sort of long tail distributions on annotation archives. So some groups have gotten up to larger category counts. They might have significantly more annotations for their targets of interest, their species of interest, but then they have much rarer things that they only have a couple annotations for. Trying to handle this in a couple of ways. One is just souped up augmentation, data augmentation, augmenting some of these channels slightly differently, especially for the categories that are less frequently. AI-assisted annotation to try to speed up annotation on new categories of interest, things like automatic box to polygon conversions, tracking targets based on a single user selection. But I think additional work needs to be performed here on the algorithm side. Done a little bit with low shot learning, so giving it a couple exemplars of a target and learning models from that as opposed to many exemplars. Shown here on the video is sort of a search interface where the user's going to supply sort of a single instance of a flounder. I'm not going to go through this in details, but if there's questions after the fact, feel free to let me know. The user supplied, an image of a flounder. The system provides some initial feedback on things it thinks are similar to that using video search. Then the user can go through, adjudicate what was right, what was wrong, give feedback to the system, press a refine button at the top, and it sort of creates a fast short pass model that can be used to bootstrap annotation to create those heavier deep classifiers, or just used as is if the model's good enough. Typically, if you have a very distinct object, it'll work well, but if you're going for two species of fish that are very similar, that's an approach where you would rely on deep learning a bit more. I guess challenge number 4 was people using multiple deep learning frameworks. To try and address this, we basically created a plugin interface where the backend's sort of coded in C++ just for efficiency, but derived classes can be performed in Python or MATLAB as well. We've definitely seen PyTorch and TensorFlow become sort of the two most paramount frameworks out there, but there's still other in use. Another one is buried or obscured objects on the seafloor. Particularly, we get this on the northeast U.S. a bit. You get flounder buried in sediment. On the scallop problem, for scallop detection on the seabed, some biologists are interested in sort of swimming scallops versus buried scallops, just because some might be bycatch, especially in the case we have a clapper, so a dead shell. But basically here we've been working on, in collaboration with Quantification Farm Foundation, taking our depth maps from calibrated stereo cameras and fusing those into object detectors for improved performance. These are my last 2 slides, but secondly, we've seen a lot of specialized needs across different applications. There isn't always a one form fits all. Some people need custom development, but stereo measurement comes up a lot. Some of the more obscure ones, though, are multi-camera systems. These might be onboard looking at the same scene. They might be aerial. In the case of some of the Arctic surveys, they do a combination of optical, infrared, and ultraviolet, just for some of these seals and polar bears. Full frame classification, that's another application that comes up in a couple domains, either for background classification or substrates. Similarly, 3D modeling matters a bit more when you're trying to do duplicate suppression on some of these aerial scenes, where the frame rate between video sequences might not be super high, and the scene geometry might be very 3D as opposed to just planar, and you don't want to duplicate count your sea lines. So they come up in a few domains. Typically on some of that higher res aerial imagery, it has a lower frame rate, so we perform registration-based tracking as opposed to appearance-based tracking to not duplicate count those seals. Lastly, is running on hardware-constrained resources and embedded platforms. We've been working on an open source hardware system. This is performed by my colleague Matt Brown, called ADAPT, which is basically a combination of a low swap NVIDIA hardware camera systems, for running on the platform itself. Some people are fine just taking their data, bringing it back to the lab, doing analysis on it in the lab, but others want to do it closer to the source. Use the algorithms to actually decide which data you're keeping, which you're rejecting, and this is a system targeting that. So lastly, I just want to thank NOAA ASI for funding VIAME, a couple of the groups, CFF Riverside, some image annotators and testers across a few organizations. So if you're interested in following up, definitely check out our website or send me an email.
SICAPTOR, monitorización electrónica para una mejor gestión.